Started talking about mathematical statements and the logical connectives that we use to build up more larger, more meaningful statements, including ands, ors, negations, and implications. And so today I want to just go through and define each one of these a little bit more carefully and talk about how we know different statements of these types are true. We already maybe have a kind of an idea in our head of when these statements are true, but we're going to make that rigorous today. So the first type of logical connective we're going to talk about is a conjunction. So if P and Q are some arbitrary statements, assume P and Q are arbitrary statements throughout here. We would say that the conjunction of P and Q, which we denote P, this is a little wedge in the middle, it's like an upside down V, Q, we read this as P and Q, and just like that problem we saw in the warm-up, this is going to be a statement which is only true if both parts, both P and Q, are true. So we would say this is a statement which is true whenever both P and Q are true. Right? Keep in mind, because P and Q are arbitrary statements, each one has a truth value, which means P could be either true or false, and Q could be either true or false. And so there's 4 different possibilities, right, 2 for P and 2 for Q, of combinations of truth values for an arbitrary conjunction of the form P and Q. But we're going to say that that conjunction is only true when both parts of it are true. Right? So as an example, if we look at the statement, all natural numbers are positive, and 5 is an even number. Well, this is going to be a false conjunction overall. Right? We can sort of diagram this. We can turn this into symbols by calling this first statement P. So P would be the statement all natural numbers are positive. Q would be the statement 5 is an even number, and it's connected with an and, which we use that little wedge symbol for. All right? So overall, P is going to be true. All natural numbers are positive. Natural numbers are 1, 2, 3, 4, etc. But the statement Q would be false here. 5 is not an even number. It's a false statement. And so overall, this whole conjunction we would consider to be false. So we would say the entire and statement is going to be false because we need both the P and the Q part to be true. Now, a good way to keep track of this, because there's 4 different combinations of truth values that arbitrary statements P and Q could have, would be in something that we call a truth table. Right? So P could be either true or false, and Q could be either true or false, which means our different combinations would be both true. P is true, Q is false. P is false while Q is true, or they're both false. Right? These are the 4 different combinations you could have for true and false statements. And so the way that we're defining this conjunction, P and Q, it's only going to be true when both parts of it are true, when both P and Q are true. Otherwise, the conjunction is false. So this truth table, that's what we call this, is just a way of laying out really carefully all the different scenarios or all the different possible truth values of P and Q and what that would mean for the truth value of the conjunction. All right, this is going to be a handy tool when we start looking at more complicated mathematical statements that maybe have multiple different logical connectives, ands, and ors, and negations, etc. Okay, with that in mind, let's move on to our next logical connective, which is a disjunction. We say the disjunction of P and Q, which we denote with P, V, Q, so this is like a V symbol, and we read it as P or Q. Well, this is an or statement, and we saw in the warm-up that an or statement is going to be true as long as at least one part of it is true, right? Either P needs to be true or Q needs to be true, but it's going to be an inclusive or, which means if they're both true, then the whole statement is also still going to be true. So in particular, this is a statement which is only false when both P and Q are false. If at least one of them is true, then the entire or statement, the entire disjunction is true. So if we look at the statement, all natural numbers are even, or 5 is an even number. Are all natural numbers even? No. 1, 3, 5, these are all counterexamples. So this first part, let's call it P or Q. This first statement P is false. The second statement Q, 5 is an even number, that's also false. So overall, this OR statement is going to be false. Because in order for an OR statement to be true, we would need at least one of these to be true. They're not, and so this entire statement would be false. And again, we can keep track of this a little bit more carefully in a truth table. We have P, Q, P or Q. All right, well, I'm going to lay this out the same way I did the last one. This is a conventional way to do it. Start with true, true, false, false, and then alternate true, false underneath the Q. This gives you every possible combination of truth values for P and for Q. And we said that P or Q is going to be true as long as at least one of the base statements are true. Okay, so P is true here. In fact, they both are, but as long as at least one is, the entire OR statement is true. In the second case, P is true, so at least one is true, so the OR statement is true. In the third case, Q is true, so the OR statement is true. But in the last case, when both P and Q are false, the OR statement would be false. Because remember, an OR statement is only false when both P and Q are false. So our truth table for this disjunction would look like this. Okay, so one thing to keep in mind, let me just reiterate it here. We use an inclusive OR, which means they could both be true. So I could say something like, 2 is an even number, or 5 is a prime number. Right? It's not exclusive. We're not saying one or the other. We just need at least one to be true. And so, in fact, in this case, P or Q, P is true, and Q is also true. So if we refer back to our truth table here, when they're both true, the OR statement is also true. I'll just write it underneath the OR sign. The whole thing is true. Okay. So let's look at our next logical connective that we can use. The next one is called a negation. So we say that the negation of a statement P, and we denote it in two different ways, and I'll use them interchangeably because they're both very common. One of them looks like sort of a squiggle, a tilde P, and the other looks like kind of a negative sign with a little tail on it, right? And we read that as not P. This is a statement which has the opposite truth value of P. So the negation of P is going to be true whenever P is false, and the negation of P is going to be false whenever P is true. So not P is a statement which has the opposite truth value as P. Okay, so if we look at the statement P, which says pi is less than 3, the negation of that would be it's not the case that pi is less than 3. But we can rewrite that by saying if it's not the case that pi is less than 3, then that would mean that pi has to be greater than or equal to 3. Okay, notice that for any arbitrary statement P has some truth value, true or false. Its negation is going to have the opposite truth value, which means for any two statements of the form P and not P, exactly one of them will be true and the other will be false. Well, is pi less than 3? No, it's 3.14, right? So this is false. And so the negation would have to be true because they have opposite truth values. And indeed it is. Pi is greater than or equal to 3 because it's 3.14-ish. All right, and so the truth table for this is actually pretty simple. Usually when we're writing a truth table, we have a P and a Q, so we have 4 different truth values for the combination of P and Q. But this time I only have one base statement, which is just P. So that statement P is either true or it's false. So our truth table only has 2 rows here. But the negation of P then needs to have the opposite truth value of whatever P was. So if P were true, then the negation would be false. And if P were false, then the negation would be true. So we have this very simple truth table here. Maybe this is a good time to mention when you have just a single statement P, base statement P, your truth table has 2 rows. And if you had a statement with both P's and Q's, we know that we would have 4 rows, right? True, true, false, false, true, false, true, false. What about if you had 3 base statements? What if you were trying to build up to some conjunction like P and Q and R, for instance? Well, using the multiplication principle, there's 2 possible truth values for P, 2 possible truth values for Q, and 2 possible truth values for R. So there's 2 times 2 times 2, or 8 different combinations of truth values. And so if we needed to draw a truth table for this, it would be pretty complicated. It would have 8 rows. Right? So we would start off by doing true, 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 false, 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 under the P column. Then we would alternate true, true, false, false, true, true, false, false, under the second column. And under the third column, we would alternate every time. True, false, true, false, true, false, true, false. It's just something to be aware of. If you want to make sure that you actually list out all the different possible combinations, this is the standard way to do it. You start off with 4 T's and 4 F's, then you alternate 2 T's and 2 F's, and then you alternate T's and F's every time. Okay, so this covers negations. Our next type of logical connective, which we saw in problem 3 in the warm-up, is a conditional statement or an implication. So we define this as a conditional statement or an implication from P to Q, and we denote it with an arrow like this. Sometimes you'll see just a single arrow and not a double arrow. It means the same thing. And we read that statement as if P, then Q. Or sometimes we read that as P implies Q. This is going to be a statement which is true if whenever P is true, Q must also be true. Right? If it's the case that, it is the case that whenever P is true, Q must also be true. Right, so this is a statement wherein if the first part is true, then the second part is automatically true as well. And we call that first part, we call the P, the part before the arrow, the hypothesis of the implication. And we call Q the conclusion. So as an example, let's look at the statement, if it rains today, then I will go to the movies. Or let's assume this is a true implication. It's true that if it rains today, then I will go to the movies. Well, the hypothesis here is this statement right here after the if. It rains today would be the statement P. And the conclusion, the part after the then, is I will go to the movies. So we would diagram this as P implies Q, where P is the statement that it rains today, and Q is the statement that I will go to the movies. Right, so this P we call the hypothesis, right, the part before the then, and the Q is the conclusion, the part after the then. Okay, so an implication is true if it's the case that anytime the hypothesis is true, the conclusion is also true. Right, so this would be true as long as if it does rain today, you do actually go to the movies. That's what would make this implication true. Now let's think about what that really means if we were to draw a truth table for this. Right, so the possible truth values for P would be true, true, false, false. And for Q would be true, false, true, false. Make sure you can actually read this. Okay. All right. So we're saying that the implication P implies Q is going to be true if it's the case that whenever P is true, Q must also be true. Okay, so if P is true and Q is also true, that makes this implication true. But if P is true and Q is false, right, if it rains today and you didn't actually go to the movies, then that implication would have been false as well, right? So when P is true, true hypothesis, false conclusion, that makes the entire statement false. This leads to an interesting question. How do we define the truth value of this implication if the hypothesis, the first part, isn't true? Like if it doesn't rain today, how would you know whether this implication is true or not? Well, the thing to keep in mind is that this statement, this P implies Q here, it didn't really assert anything about whether it rains today or not. It didn't say whether you were going to go to the movies or not if it didn't rain. All it's saying is if it does rain, then I'm going to go to the movies. So we say that if it doesn't rain, well, this statement really didn't make any promises here, so it doesn't matter whether you go to the movies or not. In other words, the conclusion doesn't really matter. If the hypothesis is false, we would say that this entire implication is vacuously true, just because it didn't really make any promises if the hypothesis is false. Okay, so notice, if the hypothesis is false, that's the P part, the whole implication, P implies Q, is automatically true. Whether the conclusion is true or false, the whole implication is going to be true. This is a hard one to remember when you're first learning it, right? But anytime the hypothesis is false, the entire thing we say is vacuously true, right? And so the other key thing to notice here is if we look at the truth table for P implies Q, it's only false in one case. It's only false when the hypothesis is true and the conclusion is false. P implies Q is false in just one case. And that's the case where the hypothesis P is false and the conclusion Q, oops, sorry, my bad, I read this wrong. When the hypothesis P is true and when the conclusion Q is false. Right, so this is a good thing to remember when you start filling in truth tables for more complicated statements. An implication is only false when the first part, the hypothesis, is true, but the second part, the conclusion, is false. Otherwise, the entire statement is going to be automatically true. All right, with that in mind, let's talk about our last logical connective, which is related to a conditional statement or an implication. We call this a biconditional. So a biconditional of P and Q, and we denote it with a double directional arrow, so it's an arrow pointed both ways. And again, you might see it just like this. We read it as P if and only if Q. And this is a statement which is equivalent to saying, or which really means, that P implies Q and Q implies P. This is really how it's defined. It's a conjunction of these two implications, right? It's two conditional statements. P implies Q and Q implies P. In other words, if P is true, then Q is also true. And if Q is true, then P is also true. So a biconditional statement is a statement which is true, right? P if and only if Q is true if, well, okay, actually let's fill out the truth table first, and then we'll come back and try to finish this here. All right, so let's, for example, look at the biconditional statement. Today is Tuesday, if and only if and only if looks like this, tomorrow is Wednesday. Right, so this is P if and only if Q. Is this a true biconditional statement? Well, we would need to check that P implies Q is true, and we would need to check that Q implies P is true. So P implies Q would be the statement, if today is Tuesday, then tomorrow is Wednesday. This is a true statement. If today were Tuesday, it's not. For me, it's Saturday. If it were Tuesday, though, it would be true that tomorrow is Wednesday. So that first conditional statement is true. And the second conditional statement, that's where we're reading it backwards. Q implies P. If tomorrow is Wednesday, then today is Tuesday. That's also true. If tomorrow were Wednesday, then today would have to be Tuesday. And so since both of these are true, that means the biconditional statement is also true. So this is a true biconditional statement. But we can build up the truth table for P if and only if Q using what we already know about conditional statements, right? P implies Q, we know what their truth table looks like. And conjunctions and statement, we know what those look like as well. So I'm actually going to build up this truth table to figure out just exactly what the column should be for P if and only if Q. All right, so our different combinations would be as follows. Now we know from the last page that P implies Q has a truth table as follows. True, false, true, true. Right? Remember, a conditional statement, P implies Q, is only false when the hypothesis, in this case P, is true, and the conclusion, in this case Q, is false. So it's false in the second case, but it's true otherwise. Now this is a biconditional, so we also want to find the truth values of Q implies P. All right, now we've swapped our hypothesis and our conclusion. So Q is our new hypothesis, and P is our new conclusion. All right, so in this case, Q implies P. In the first case, we would have a true hypothesis and a true conclusion, so the whole thing's true. In the second case, in the second column or row, we have a false hypothesis. Remember, anytime the hypothesis is false, it doesn't matter what the conclusion is. Hypothesis is false, that means the whole thing is vacuously true. In the third case, our hypothesis is Q, that's true, and our conclusion, P, is false. We said if you have a true hypothesis and a false conclusion, the whole thing is false. And finally, in the last case, Q, the hypothesis is false, so the entire statement is vacuously true. All right, and finally, we can build up to P if and only if Q, which is really just saying P implies Q and Q implies P. Right, that's how we've defined this biconditional. So this is an AND statement where the first part of your AND statement is, oh, I've used this color already. The first part is P implies Q, and the second part is Q implies P. So to find the truth value of this AND statement, we need to look at the column for P implies Q, and we need to look at the column for Q implies P, and we need to use our rules for an AND statement. An AND statement is only true when both parts of it are true. Okay, so in this first case, both P implies Q and Q implies P are true, therefore the AND statement would be true. In the second row, they're not both true, because this first P implies Q statement is false, right? And an AND statement is only true when both parts are true. Therefore, the AND statement would be false here. Similarly, in the third row, they're not both true because Q implies P is false. Therefore, the AND statement is false. But in the last case, they're both true again, which means P if and only if Q is true. All right, now we can go back and compare what we see in the last column here to the actual truth values of P and Q. What we notice here is that the if and only if statement, the biconditional statement, P if and only if Q, is true in the first case and the last case. It's true when both P and Q are true, and it's true when both P and Q are false. That makes sense, right? If we look back at this if and only if statement, today is Tuesday is a false statement. Tomorrow is Wednesday is also a false statement because today is Saturday and tomorrow is Sunday. So this P if and only if Q is true when both parts of it were false. But it's also true when both P and Q are true. And so we can say that a biconditional statement is one that's true if P and Q have the same truth value as each other. If they have different truth values as each other, then the if and only if statement would be false. So these are our different logical connectives, and in the next chapter we'll try to use those to look at more complicated statements and see how do we determine whether they're true or false.